Hey, hello everybody. Welcome to lesson 4.5, which is on powers of binomials. Okay, so binomial being a math expression with two parts, like a plus b. Binomials, if we're talking about powers of binomials, we're talking about like a plus b, that quantity squared, or a plus b, that quantity cubed, or to the fourth, or to the fifth. So we've done a lot of stuff with quadratics, where we have x squared terms, or binomials, x plus 3 squared, something to the second power. But today we're going to look more about like how to generalize that to higher powers. Okay. Um, Today's goal is to expand powers of binomials by using Pascal's triangle and the binomial theorem. So there's kind of two things that we're going to work with today. To be honest, there's quite a lot that's going to be going on today. It's going to look overwhelming at first, but hopefully we can get through and kind of take it chunk by chunk. Today's vocabulary is Pascal's triangle, so this is kind of a spoiler for later, so ignore it for now. All right, so let's look at this. With powers of binomials, you can expand binomials by following a set of rules and using patterns. Now, buckle up. This is just going to be a long list of things. We'll go through each term individually in a moment. In the binomial expansion of a plus b to the n, there are n plus 1 terms. N is the exponent of a in the first term and b in the last term. In successive terms, the exponent of a decreases by 1 and the exponent of b increases by 1. The sum of the exponents in each term is n, and the coefficients are symmetric. So this isn't like a list that you need to memorize per se, but let's go through and just look at how that list is true. We're just kind of noticing things that are patterns when you're working with these binomials getting expanded. So if you're looking up here, if we're talking about generally a plus b to some number, okay, so we have different options. We have a plus b to the 0, to the first, to the second, to the third, so on and so forth. Well, let's see if they all fit this. Okay, there are n plus 1 terms. Well, if n is 0, there is one more term than that, just a 1 over here. If n is 1, we get 2 terms. If n is 2, we get 3 terms. If n is 3, we get 4 terms. Okay, so it seems like there's a pattern where we are always getting one more term when we expand it than the power we are expanding it to. All right, n is the exponent of a in the first term and b in the last term. So if it's 0, they're both 0. If it's 1, they're both 1. If it's squared, you have an a squared and a b squared. If it's cubed, you have an a cubed and a b cubed. Okay. In successive terms, the exponent of a decreases by 1 and the exponent of b increases by 1. Okay, so as we watch a go by, we have a to the first and then no a's, a to the second, a to the first, no a's, a to the third, a to the second, a to the first, no a's. On the b's, we start with no b's and then we get 1. Start with no b's, then we get 1, then we get b squared, b to the 0, b to the first, b to the second, b to the third. Okay, so a goes down by 1 each time, b comes up by 1 each time. The sum of the exponents in each term is n, is equal to the power. Okay, so if it's second power, then we should have a second degree term here. Okay, a1, b1, that adds up to 2, b squared. If it's 3, they should always add up to 3. So a cubed, a squared plus b to the first, so 2 and 1 makes 3, 1 and 2 makes 3, 3 by itself makes 3. Okay, and coefficients are symmetric. So the coefficients, I'm not writing in ones here, but this would be 1a, 1b, 1a squared, 2ab, 1b squared, 1a cubed, 3a squared b, 3ab squared, 1b cubed. So those coefficients 1, 3, 3, 1 are symmetric. They're a mirror image down the center. 1, 3, 3, 1. They flip over. 1, 2, 1. They're symmetric down the middle. Okay, so these are all just kind of patterns that we're kind of looking to be aware of as we look at this expansion, and just imagine as we go a plus b to the fourth, a plus b to the fifth, we can kind of start to imagine some sense of what we're going to see. We'd see a to the fourth, and then a to the third, b to the first, a to the second, b to the third, a to the first, b to the fourth, b to the fifth. We'd have some coefficients out front that we don't necessarily know yet, but we know that they'd be symmetrical. Okay, so these are kind of things that we could use to just sort of imagine what would be the next expansion. Now, we're trying to learn this because the bigger those numbers are, the bigger the exponent, the faster and faster you're going to get more and more and more terms. So you have 2 first, and then you have 3, and then you have 4, and then for the next one you'll have 5, and then 6, and 7, and 8, and 9, and 10. So if you have like to the 100th power, you're going to have 101 terms, and you're not going to get 101 terms at first. I mean, like this 2ab, if you think about when you do an area model or foiling, this 2ab comes from a times b and b times a. So you have to put it together to simplify down to, 3 terms in this one. But you really start out with 5, no, not 5, but 4 terms overall in this one. 2 of them simplify together because they're like terms. So if you add something to the 100th power, you'd have, way more than 101 terms, and you'd simplify it down to 100 terms. Okay, that's a lot to do by hand. So we're going to try to figure out ways to not do it by hand. All right. Finally, we're going to skip this description about Pascal's triangle for a moment, and we're going to just look at this. So this is the binomial theorem. This is some huge, horrible-looking thing, but let's just look at what we kind of notice in here that's similar from what we just said. So if we're doing a plus b to the n, we start out with a to the n and b to the 0. Okay, so that would be like when we have a plus b to the third, we start out with a to the third and b to the 0, just one invisible there. Okay, so we start out with whatever that exponent is, and then we go down. The next one we have n minus 1, then n minus 2, then n minus 3. So let's say that n was like 10. So this would be a to the 10th, a to the 9th, a to the 8th, a to the 7th, a to the 6th, all the way until you got a to the 0. Now b would rise. It would go from b to the 0, b to the first, b to the second, b to the third, all the way to b to the n. We would just say an n was going to be 10. So it'd be all the way to b to the 10. Now this thing in the front, this nc sub 0 thing, this has to do with something called combinations. And if you haven't studied combinations yet, that's all right. We're going to get to that, but we're not going to get to it immediately. I just want to kind of highlight that all that we have left to kind of understand this general formula for, the expanded polynomial is that we just have to figure out this combination part in the front. And that really comes down to like, how many different combinations of a squared b do you get in this one? Well, you get 3 combinations. You also get 3 combinations of a and b squared. You only get 1 combination where you can make a cubed, and you only get 1 where you can make b cubed. Okay, so these coefficients out front are something that we want to be able to get a general idea of how to come up with. Once we have that, then we can just figure out any arbitrarily large exponent and what it all turns into. Okay, so we are going to move forward with that in mind. In our next video, I'll be talking about what are binomials generally and why we would ever care to multiply them by themselves over and over and over again.